Hey guys, hope you're doing well. I'm back with yet another tutorial. Uh, this time, what we're going to talk about is actually something that I've been working on for a while now, and it took me a while to sort of get this through. But what I wanted to do was sort of mimic this crumble that you see on your screen right now, right? And obviously, because Houdini 21 had some updated features in the MPM solver, I was really interested in figuring out how can, we accomplish this sort of crumble with Houdini uh, 21 version. Now, I obviously ended up doing some of my tests, which I'll show you right now. This is one of them, right? And this was the second one. Now, both of these were relatively high point counts. I think the first one was about a million, the second one was about 2 million points. So I'm gonna show you, obviously the source file is going to be provided as always, but there are a couple of things that I'm gonna talk about before we start off with what actually happens in this. Now, the first part that was the most difficult when I was trying to achieve this was locking on a preset and the behavior of the preset that I wanted to lock on. Now, I was working with chunky for a very long time, but eventually I realized that it was chunky, but the preset from here was going to be set to concrete. So I was working with snow. I tried working with soil, I tried working with mud, I worked a little with rubber as well, but sadly none of those work. But and I feel like there's very less information available on the internet as to which explains in a very layman language as to what these settings actually mean, right? So I'm just gonna quickly overgo them for you guys, and I hope I can be as clear as I possibly can. Now, starting off the density, right? What this actually means is how tightly or how loosely your object is actually packed, right? So if I, for example, raise this, wait, let me just reset all of this to default, and I'm just gonna reset all of this to the default values. And yeah, so if I just play this right now, you'll see this is what happens, right? Now, if I lower this density value to something drastically low, let's say 100, right? You'll see that this acts a lot more stiffer. And that is that what that tells you is that it does not have enough so it does not have enough points to squeeze on, right? The density is very low, right? So the lower the density, the more stiffer your object is going to behave, but also the more brittle it is going to look like, right? The second and the most important part in this whole simulation was this critical compression, right? Now, what this does is it actually dictates that once you're compressing your object, under what load is it going to break, right? So if the value is too high, right, it breaks too soon, and if the value is too low, it absorbs everything. So like for example, if I just make this value like extremely low, watch what happens. See how it just squishes onto itself, right? And if I just make this too high, watch what happens. See how it just breaks instantly the moment it touches the floor, it just breaks down. That is basically what this critical compression does, is to, as soon as the compression starts, right, it dictates the behavior of the object. So if the values are too high as soon as the compression starts, it tries to break the material apart. But if the value is too low, right, it tries to absorb that compression and squish the material. Critical stretch is exactly the same thing, but for stretching, right? Okay, this is actually an important part. Now, what compression hardening does is, let me just revert this back to the original value, and I'll just play this simulation. Now, what this compression hardening does is, if I come to my MPM solver and visualize color from attribute, okay, now if I play this, you'll see that anywhere that it's trying to detach or anywhere that it's trying to break, the color sort of changes, right? The ramp sort of changes. Now, what this compression hardening does is the lower this value is, the lower this value oops is, the less propagation of force there's going to be throughout the material. Do you see that? So it basically, I mean, I could be technically wrong, but this basically is sort of your dampening counter for how your material is propagating forces through itself, right? Now, let's see what happens if I make this bigger. You see how how the forces are spreading throughout the material more violently, right? Last thing is, sorry, the second last thing is actually the stiffness of the material, and this does exactly what it says it does. So I'm pretty sure if you're an avid user of Houdini, if you've worked with Vellum, if you've worked with different, if you've worked with other systems inside of Houdini, you're well aware of what stiffness does. I'll just raise it to show you. It basically makes the ball act like a big fat rock, right? Now, another important aspect was this volume preservation. Now, what this volume preservation does is that it actually tries to hold the material together. So, for example, watch what happens when I raise this value to an absurdly high value. I'll just see how it just splatters all over the ground. Now, watch what happens when I lower this. See, so what this volume preservation is doing is it's actually trying to hold the material together, right? And so the most important thing while working with MPM is that all of these settings sort of go hand in hand with each other. And if you meddle with one thing, right, you've got to counterbalance it by adjusting the other thing. Now, that is entirely why all of this process with the lipstick crumble took me about, I'd say, a month, right, where I was constantly researching, where I was constantly testing new values. Now, once all of this is covered out, I'm not going to talk about this because if you're working with MPM, I'm pretty sure you understand how this system works. Another thing that actually, really impacts how your simulation behaves is number one, your particle separation. So if I just lower my particle separation to something like this, I don't know if my computer is going to be able to run this, but let's see. Okay, so there you go. Now you see how the result has drastically changed as soon as I've lowered my particle separation. The other thing that actually is really, really important is, I'm just gonna raise this a little so we can get a faster playback. Yeah, that's better. Another thing that really sort of impacts over how your simulation behaves is this grid scale. So what I understood by this grid scale is the lower this value is, I mean, obviously till a certain amount, the more the lower this value is, the more detailed your simulation gets. But there's obviously a catch to it. So the lower this value is, the more time your simulation is going to require, the more sub steps it's going to need, and there's a very high chance that as soon as you're lowering this value to a certain amount, your simulation becomes unstable. So it's again, it's a counterbalance thing, it's a trial and error. You've actually got to figure out how your simulation scale looks like, and then you've got to meddle with these settings. Now, what I'm going to do is I'm going to come back to my simulation and what I ended up doing, right? I'm just gonna skim through this. I'm gonna talk about the important parts that are like I'm gonna cover the whole source file, excuse me, but I'm just gonna talk about things that help me achieve this sort of look. So first of all, this was a standard lipstick model that I got from the internet. I'm gonna attach this with the source file, right? Uh, I just scaled it down because this was imported from Cinema 4D, and Cinema 4D units do not go well with Houdini units. Uh, After that, what I did was I just gave it a connectivity node, which basically just splits both of these unconnected segments into different objects, right? So that way it's easier for me to split them, right? And that is exactly what I did afterwards. I split them, and I basically just split my lipstick because it was a hollow object. I had to fill it, and I ended up remeshing it so it had more polygons. And also, another thing that I did was, and you could, entirely ignore this, was that I sort of just gave this lipstick some thickness on the inside because I was thinking that I'm just gonna simulate the shell of it, but I, didn't end up doing that. And once that was done, I just gave this whole object some animation, right? And that is all. Now, coming back to my, this is actually the larger simulation. I'm not going to discuss this first. Let me just quickly come back. Okay. Yeah. All right. Now, another thing that once that was all done, what I ended up was I created a new container. I imported my object inside of here, and I used a time shift node to sort of freeze this. And once that was done, the reason I sort of used that time shift node was because I wanted to transform this, and I wasn't going to be using the animation that I applied to this object for this part of the simulation. But yeah, I used a match size node to sort of just rotate. I rotated the lipstick over here, and I used the match size node to sort of just match the grid where it's just above the 0 point, and then I just gave it some translation, and I use that translation to animate the whole lipstick, right? And once that was done, I used a split, right? And I used the split with the name attribute, and I separated my lipstick and the cartridge outside, right? Once that was done, now, this is actually a really good trick that I saw somewhere. And what that basically means is you don't use an animated geometry for your NPM source. Instead, you use a static geometry, right, for your NPM source. Now, if I open up my NPM source, this is going to take some time. Actually, you know what? Let me just increase my particle separation. These simulations tend to get really, really heavy. All right. Now, what you're actually going to do is you're going to import your frozen geometry for the npm source. And as you can see, I have like I've nothing being animated right now. Now, I'm gonna go over these settings in a while, but first of all, we've got to talk about how did I import my animation settings? How did I import my animation on here? Like, after that, what I ended up doing was I ended up just creating a group, right, for the same lipstick, which was animated, right? And I set it on points. I used a keep and bounding ranges through a bounding box, and I gave it a bounding box, right? So basically, what I ended up doing was that everything along with time was sort of being covered by this bounding box, and I had a group for that, right? I used a color node to color that to sort of create that mask where it's sort of, just animating over time, right? And obviously, I mean, most of you guys have already guessed that what I'm going to be doing is I'm going to be using this mask to simulate, to mix between simulation and animation, right? And how you do that is you actually create an attribute over here, which is pin to animation. It's an integer, right? And what an integer basically is that it does not have decimal points, so it's a whole value, right? And it's an integer value. And what that does, it tells Houdini if something is supposed to be simulated or animated, right? Now, in my npm source, I've already checked pin constraints, right? And I've used initialize as pin and enable animation, right? So what that tells Houdini is that this geometry is actually going to be animated, but because there's no sort of animation on this right now, nothing's gonna happen. So for example, if I turn this point deform off and I come to my npm solver, if it lets me, you'll see nothing over here, right? Because everything for Houdini is actually it should. This is buggy, man. I don't know what the problem is over here, but anyways, but yeah, coming back. So this actually tells Houdini what part is animated and what part is not animated. Yeah. So what this does is that it actually tells Houdini about what part is animated and what part is not animated, right? Now, once we've got that out of the way, what we do is we use that animated geometry, right? And we copy that animation onto this npm source node that we have. And essentially, in its very essence, what this npm node is actually doing is it's just using a points from volume, right, to create this whole geometry over here. I'm just gonna give it some time to run, and I have no idea why this is so slow, man. Yeah, there you go. There we have it. Now, there you go. So we have our geometry, which is animated, right? This is my npm source, which is animated. Now, the next thing that I do is I've actually copied the animation over here. The next thing that I want to copy is the pin to animation attribute, right? And when I just sort of, oh my God, this is slow. Okay, what this does is when I actually check on the pin constraints over here in the npm source, it creates an attribute with pin to animation, right? And it's an integer value. And if I come up to my npm source right now and I open the geometry sheet, you'll see everything is set to 1. And 1 means that everything is going to be animated and not simulated. Now, once I open up my pin to animation attribute transfer, where I've transferred that attribute from this point triangle that I created, if I open up my geometry sheet, you'll see now there's a difference in there, right? So that is in essence how you transfer your animation from a static geometry, sorry, from an animated geometry to a static npm source, and that is how your animated npm source would be sort of, simulated. Now, coming back to the npm source node, where I'm going to talk about some settings that I use. So what I ended up using was a concrete preset, right? I set the behavior to chunky. The density that I used was 2400, right? The critical compression was pretty high, right? I used a value of compression hardening for 3, stiffness was zero point 0.6 at 1 raised to power 7 zeros, and the volume preservation was set to 0.25. And what that did was it gave me something that looked like this. Now, one important thing to note over here is that this was simulated at around a million points, and I feel like these points are still not enough to give me a decent post-processed result. Now, I might be wrong over here. I might be doing something. Uh, my post-processing workflow might not be as finessed as someone else's, but I just didn't feel like this gave me a good output. Now on the other hand, but also in comparison, talking about the time, this sort of got simulated in about around an hour and a half. And what I ended up doing, my grid scale was obviously set at 1, and this was simulated at 0.0012. Now I ended up halving this value to 0.0006, and I actually have a cache for that. And this is actually a very heavy cache, and like this takes time. And I think I ended up simulating like 13 frames or 14 frames in about 16 hours, right? So you can see the time that it takes, but the detail on here is absolutely amazing, right? Can you see that? In comparison to this cache and here, right? The detail is absolutely ridiculous, right? Now, once I had all of this cached out, it was just a pretty standard MPM surface node to convert this back to a polygon mesh, and this being used to render and to texture. Now, I've done pretty much the same exact thing in my this simulation. It's just that this part actually had two lipsticks that were facing each other, and they were sort of colliding onto each other. And remember the animation that I used over there. Let me just open up that animation. So this animation where this is one lipstick and this is the other lipstick. So this is what I actually ended up doing, where one lipstick ends up colliding with the other lipstick, and this was all like all of this mess that you see down here for the meshing. This was just so that I didn't have to simulate it until they actually touch each other, and all of this over here was animating the part that was happening before the simulation started. Once you go through the scene file, you'll understand what I mean. Now, if I go through the npm cache for this was actually a pretty long cache as well. This took me, I think, about 12 hours to cache this out, and this was simulated, I think, from frame number 21 till frame number 60, 62. And this is right, there you go. This is what this looks like, where the two lipsticks sort of colliding with each other. The MPM configuration is exactly the same. It's just that because there are two different objects, two different active objects colliding against each other. It looks this big, but all of this is the animation part of it, right? Where I'm mirroring it, where I'm sort of just creating that pin to animation attribute, transferring it on each other. I'll attach the source file and you guys can go over this. But yeah, that is pretty much it for today, and that is how I ended up with something that looks like this. I know the detail isn't there yet, but again, that is because of the lower point count, and I would want to, see how this looks with a bigger point count. So let me know if you guys have any more questions, and yeah, I'd be happy to answer them. Until next time, thank you. Cheers. Bye bye.